In this module, we will first introduce some basic concepts of statistical thermodynamics. Then, we will demonstrate how statistical thermodynamics helps us interpret the concept of entropy and spontaneous change. Entropy is often considered the most misunderstood concept of thermodynamics. Up until now, we have discussed entropy within the framework of classical thermodynamics. In classical thermodynamics, the concept of entropy is largely based on the work of Rudolf Clausius in the 1860s and was originally derived from the analysis of heat engines. However, later developments in the field led to the introduction of statistical thermodynamics, which is our focus from this point forward. This branch of thermodynamics provides a statistical interpretation of entropy based on the behavior of systems with a large number of particles. Statistical thermodynamics employs statistical methods such as probabilities, distributions, and averages to help us understand the microscopic behavior of systems. Using these methods, statistical thermodynamics derives macroscopic thermodynamic properties such as internal energy, enthalpy, entropy, and others from the microscopic perspective of matter. It also allows us to calculate thermodynamic properties of substances, for example by using structural and spectroscopic data. Statistical thermodynamics connects microscopic molecular behavior of matter with observable macroscopic properties that are considered in thermodynamics. This approach provides deeper insight into the molecular origins upon which the concepts of classical thermodynamics, such as energy and entropy, are based. The key concept of the microscopic perspective in statistical thermodynamics is a microstate. A microstate is the exact state of every particle in the system, described at a given time in as much details as possible. For example, in a system of gas particles, a microstate would give us the exact location and velocity of each gas molecule. In a quantum system, it would summarize the exact quantum state of each particle. Knowing the microstate means we have the most complete information about every part of the system. While this level of details provides a full microscopic description, it is something we can hardly measure directly. Another concept reflecting the microscopic perspective in statistical thermodynamics is the configuration. A configuration refers to the general arrangement of particles within a system without specifying the exact details of each particle's state. It's a way of describing the overall distribution of particles or energy while leaving out the specific arrangement of each individual particle. For example, in a quantum system of atoms, a configuration would tell us how many atoms are in each energy level, but not which specific atoms are in a particular state. In this sense, we can say that the configuration lies a level above the microstate in terms of the generality of the system's description. Going even further in the scale of generalization in statistical thermodynamics, we introduce the concept of a macrostate. A macrostate in statistical thermodynamics refers to the overall state of a system described by a few quantities such as pressure, volume, temperature, or internal energy. These are properties that can be either measured directly or derived from the measurement. They describe the collective behavior of the system without needing to know any details about individual particles. The macrostate of a system is what we observe from the outside, and it is the level at which classical thermodynamics operates. The key idea in statistical thermodynamics is that it derives macroscopic quantities by analyzing the probability distribution of configurations and microstates that correspond to the same macrostate. Let's now turn to the central postulate of statistical thermodynamics, or the principle of equal a priori probabilities. It states that for an isolated system, every microstate occurs with equal probability. By using this principle, we assume that there is no reason to believe that one microstate is more probable than another within a system which is not influenced by external factors. While we cannot verify it experimentally, this principle has proven to be a powerful tool. Statistical thermodynamics, built on this assumption, can accurately predict macroscopic properties such as temperature, pressure, and entropy from the microscopic behavior of particles. Building on this principle, we can now analyze probabilities associated with different configurations, general arrangements of particles within a system. The probability of a configuration occurring depends on how many specific microstates, specific arrangements of particles, can generate that configuration. This number of microstates is referred to as the weight of the configuration and denoted by W. The weight of a configuration is proportional to the probability of the configuration occurring. The greater the number of microstates corresponding to a given configuration, the more likely that this configuration is realized. Therefore, configurations with higher weights are more probable because there are more ways for the system to be in one of their associated microstates. Next, we logically arrive at the concept of the dominant configuration. This refers to the configuration with the largest weight. It means that it is associated with the greatest number of microstates and therefore has the highest probability of being observed. Since more microstates correspond to it, it is statistically more likely for the system to be found in that dominant configuration. Thus, this configuration is what the system will most likely adopt under equilibrium conditions. For large systems, the dominant configuration has an overwhelmingly larger weight than any other configuration. As the size of the system increases, the probability of observing other configurations becomes negligible. Because of this, the system is almost always found in the dominant configuration, making it the one that primarily determines the system's properties. Thus, in large systems, the dominant configuration is the microscopic representation of the system's macrostate and effectively dictates its macroscopic behavior. Ludwig Boltzmann, one of the pioneers of statistical thermodynamics, provided a groundbreaking interpretation of entropy in 1877. He established that entropy is directly linked to the number of microstates corresponding to a system's most probable, the dominant configuration. Boltzmann expressed this relationship using his Boltzmann formula: S equals Kb times the natural logarithm of W, where S is the entropy, Kb is the Boltzmann constant, and W is the weight of the dominant configuration, or the number of microstates corresponding to it. The Boltzmann formula highlights the statistical nature of entropy. The entropy calculated from it is referred to as statistical entropy. The formula connects the macroscopic property of entropy, as known from classical thermodynamics, to the microscopic behavior of a system's constituents. The Boltzmann formula for entropy is one of the most iconic equations in statistical thermodynamics. It was so fundamental to the field that it has been inscribed on Boltzmann's gravestone, as shown in the image here, honoring his groundbreaking contribution to statistical thermodynamics and to our understanding of entropy. The key insight from Boltzmann's equation is that entropy increases as the number of microstates available to the system increases. The more microstates correspond to the dominant configuration, as dictated by the given macrostate, the higher the entropy. Ludwig Boltzmann formulated that the transition to thermal equilibrium and the associated increase in entropy corresponds to a transition from a less probable state to a more probable one. This means that, for example, if a system can exist in two possible states, it will naturally evolve from the less probable state to the more probable one. If you think about it, this development sounds entirely logical. Therefore, the tendency to evolve toward the state of maximum entropy is a direct consequence of statistical principles. This tendency provides an explanation why entropy increases in spontaneous processes. Introductory chemistry courses, as well as some simple explanations, often associate entropy with the disorder or randomness. This simplified version of Boltzmann's explanation relates directly to the concept of microstates. What is perceived as disorder is actually the dispersal of matter and energy into a high number of microstates. The statistical reason behind spontaneous processes is often simplified as a tendency of the system to increase its randomness or disorder. This corresponds to the system moving to a configuration with more available microstates, resulting in higher entropy. While not scientifically precise, this is still a useful, intuitive picture.